Now, we're happy to welcome our first speaker, Dr. Aaron Boley. Dr. Aaron Boley is an associate professor in the Department of Physics and Astronomy at the University of British Columbia. His research explores a wide range of topics, including planetary dynamics, astrophysical disks, meteoritics, space sustainability and security, and the space policy. Before joining the faculty at UBC, Boley was a NASA second postdoctoral fellow at the University of Florida and a postdoctoral researcher at the Institute for Theoretical Physics at the University of Zurich. He's the co-director of the Outer Space Institute and co-author of Who Owns Outer Space? International Law, Astrophysics, and the Sustainable Development of Space. The presentation title is Stresses on the Earth's Space System from LEO Satellite Systems. Dr. Boley, over to you.
Thank you so much for hosting this webinar and for inviting me to take part in it. Excellent. So I want to talk about the Earth space system moving forward, because if we're going to have innovation within LEO and continued use of the space environment, we have to understand how that use impacts the Earth space system so that we can continue to move forward. Now, I want to emphasize from the start that there is great recognition that satellite systems have had tremendous benefits, societal impacts on humanity. And I chose to show this COSPAS SARSAT image just to give the LEO to GEO picture. And as we continue to build with LEO systems, that promise continues, as was already highlighted in the introduction. Now, as we move forward, it is quite possible that we can do this in a very responsible way. But I hope I don't have to argue too hard that it is also quite possible that we do this in a very bad way, that we cause substantial damage, not just harming the environment, but also harming our ability to safely and responsibly use outer space. And so innovation is not going to come from just throwing up as many satellites as we can to do as many different things, but to do that in a way that ensures that we do not actually harm the Earth space system in a way that's detrimental for us, as well as the ecological system on Earth. Now, what do I mean by this Earth space system? So, there is a slowly growing recognition that space is an environment. We don't have to argue that Earth is an environment. But what is, I think, harder for people to realize is that there is actually then a connection between the two. At the most fundamental level, you have to go through the Earth environment to get to the space environment, and activities that are taking place in the space environment are affecting already the Earth environment. Stresses in one area can affect other areas, either directly or indirectly. Now, we could come up with solutions to address some of those challenges, and those solutions might be able to have a positive effect on some other areas in the environment. But it is also possible that those solutions actually hurt other areas. And in fact, one of the things we see particularly with the Earth space system, is that we try to solve one particular problem, say casualty risks, and we create a new problem, such as dumping a lot of material into the upper atmosphere. We're going to talk about that more. Another issue to keep in mind is that because it really is a system, it has a rough state. And that state can transition very rapidly from one to another. And once it goes into another state, our experience of what we have in the current situation just may not be applicable. All right, so Earth space sustainability is a term that's getting thrown around quite a bit, and everyone means something a little bit different when they say sustainability. It could be economic growth, it could be environmental, it could be very orbit specific, And these are all just some examples. For this talk, when I say sustainability, I'm talking about the responsible use and exploration of outer space, and that responsible use and exploration also includes environmental stressors, or at least accounting for them. I am not going to assume, and I don't think we should assume, that we can just develop the orbital environment indefinitely without having consequences for doing so. And we need to think both near term and long term for any type of changes we have in that particular in the system. And this is one of the hard things to recognize, is that it will require compromises. We won't be able to do absolutely everything we want to be able to do, at least in the way we want to do it. And so it's going to have to create, the innovation is going to have to come in both the development of the systems as well as the interaction of the LEO satellite systems with Earth and space. And so here are a couple kind of symbols that are used to denote the different pillars of sustainability, the Earth space sustainability system. And so we have dark and quiet skies, casualty risks, emissions, and by emissions, I mean both from launches and reentries. We'll get into that. There are, of course, space security issues that come into play here. Space debris, we're going to hear a lot more about that from other speakers. And then, of course, there's the non-appropriation and equitable use. And so the space is also a resource. And as you start consuming that resource, you limit the ability of others to use that resource. And so this comes down to international law as well, as applied to space, what we loosely call space law, and the concept of how you actually can use a particular area of space without appropriating it. And that is an ongoing discussion within the international community. This graphic from the Government Accountability Office in the US nicely summarizes kind of some of the challenges we have with interactions with the Earth space system. So, of course, we have rocket emissions, but then we also have reentry emissions. We have systems in outer space, and those systems are providing a service, say satellite internet, but that service can also affect radio telescopes. Sunlight can affect optical telescopes. The reentry over here may not demise entirely in the atmosphere and create a casualty risk for people on the ground, ships in the ocean, or even aircraft in flight. And of course, the one area in which I think there is very strong recognition of the space environment actually being an environment is with the problem of orbital debris, because that's directly operational and people have been having to contend with that. But there are many other elements besides orbital debris that we have to consider. All right, so humanity has been really, really ramping up our launches. And so this is just the launch rate over time broken down by countries/regions. And we see the sudden spike here. This is then with the development of things like Starlink. But then there's just also greater use by other states. And all of this is going to come into play, and we expect this to keep growing. And with that, we expect the orbital environment to become more crowded. We expect a lot more emissions to arise from that as well. Now, this does not account for things such as space tourism that we'll also have to contend with, and also just major orbital systems. So think about on-orbit manufacturing, the possibility of having solar-powered arrays in outer space and so forth. So there are many other elements that are not reflected yet on this particular chart. But one of the things that you should take away is that there's every expectation that the launch rate is going to continue to grow. And even if we have some of these massive rockets that come online with just absolutely huge heaves into LEO, that's still going to be dumping a tremendous amount of emissions into the atmosphere in order to launch that amount of mass. So it just go from one huge injection instead of a bunch of small injections. Of course, many of you do not need to be reminded of this plot, but I just want to show it just to make sure we're all have this mental image of what low Earth orbit looks like at the moment, at least in a very average sense. And so the The blue here is showing you the track debris. And of course, this region here is a result of the largely of the Chinese ASAT test, as well as the Iridium Cosmos collision. There was a spike down here as a result from the Russian ASAT test. Luckily, most of that has deorbited. It did take some time. But things to note here is that we have rocket bodies that are distributed throughout LEO, and of course, they are on elliptical orbits. Many of them are on elliptical orbits, so everything that you see here is averaged according to the time it spends at its particular orbit. So that's how these densities are created. And we see these very strong spikes here within the payload, and these are the construction of the so-called mega constellations. So here's the Starlink system, and then we have OneWeb here. And the final plot that I just want to show to give a snapshot of how things are changing is that this is the satellite hockey stick plot. And so, of course, here are the objects in orbit that we track. Of course, this is just the trackable objects. There's, of course, many, many more times things that are not trackable, at least consistently so. And of course, a real danger is the lethal non-trackable debris. But I'm going to set that aside. Here's the fragments that we know of that are trackable. But the orange plot, or the orange curve here, is showing then the change in the payloads. And we've launched more satellites in the past 6 years than we have in the past 60 years. And so we're just rapidly changing the type of operational environment that we're used to. And this is going to create considerations for not just operations, but then also how we're affecting the environment, because the rate of our space use was much lower. Now, for moving forward with this talk, there are just 3 items that I want to focus on. And the other ones are absolutely important, but I have to pick a few to just for the sake of time. And then also things like orbital debris will be discussed further in the panel. All right. So dark and quiet skies. One of the things that I really want to emphasize is that the fundamental way that humanity explores space is through astronomy, just through observations from Earth. Yes, we have space systems that also do this, but ultimately the backbone of space exploration is astronomy. And so there is an importance moving forward from satellite operators to ensure that we could continue to have that fundamental connection with exploration, and also further the interests of all space users. As we change the sky, we are not just making the astronomy more difficult, but there are actual natural heritage issues, cultural heritage issues. Certainly, there are science opportunities that become lost. And there are actually pretty important scenarios in which we need to ensure that we're able to detect faint objects, and that's for things such as planetary defense. The Chelyabinsk event, if you recall that from 2013, where you had just a 19-meter wide asteroid enter suddenly, unexpectedly, and blow up over the city of Chelyabinsk, sent 2,000 people to the hospital from broken glass, around 2,000. And our first line of defense is detecting such objects so that we can actually have then a civil defense, such as warning people about it, in place. Now, it's not just streaks that are of concern, but things like the overall sky brightness, so that there are aggregate effects for what we're actually doing, and that needs to be taken into account. And particularly if we produce a lot of debris in orbit, then debris production is not just a problem for operations, but it's actually enshrouding then Earth in a dust cloud, and that raises the overall brightness of the sky. And that's something that we absolutely need to avoid doing. For the casualty risks, this is something that I think is being recognized more and more. It was always there at a lower level, but it is increasing. And so we see things like pressure vessels that are crashing into this person's farm here. This is in the South Asian Pacific. This is then another pressure vessel that landed in India. Here is then a ring from a rocket body landed in India. We have the Crew Dragon trunk that or the Dragon trunk that crashed in Australia. And then most recently, we just had that battery pack that was jettisoned from the ISS and re-entered, and it had a part of it that went through somebody's home. So kind of one of the assumptions for a lot of casualty risk is that at least people in the global north are sheltered. And so, there's not going to be a problem. Well, this is a pretty striking image to show that that's not true. It went through the roof, then went through the ceiling, then it went through the floor, and then embedded into the person's groundwork. So like this is a pretty serious event. And the calculations for this is that we're kind of at the rate now where we're expecting, possibly a few % chance of having a casualty each year, and that's going to grow if we're not careful. So there actually needs to be strong considerations for a controlled reentry regime, at least for the very massive objects. So we just can't abandon rocket bodies in orbit. Now, it's not just the casualty risk that's the problem, but there's actually serious economic disruptions. And so we're seeing kind of the space industry come head to head now with the aviation industry. And so this happened fairly recently when there was an uncontrolled reentry. And on one of the predicted final orbits, a very large object was going right through some European airspace. And Spain and France made the call to close airspace. And it was actually rather sudden and very disruptive. You could criticize that particular decision, and there is a very good debate that needs to be had about what are the thresholds for doing this. But the fact is that aviators or people in charge of aviation safety are having to make decisions based on many unknowns about where massive things are going to re-enter. And just a 300-gram object at altitude can take out a 777. And by take out, a massive depressurization, total loss, 300 people killed. Very low probability event, but very high consequence. Okay, so for emissions, this plot nicely summarizes a lot of the things that we're dealing with. Certainly you have exhaust that's close to the ground in the troposphere, the part of the atmosphere that we often think about, this part that has what we think of as weather. But actually a huge amount of the emissions take place above the tropopause and take place in the stratosphere and mesosphere and even in the thermosphere. And this is where we can have some very kind of interesting physical effects that also could be very problematic. And it's not just the rocket emissions, but it's also then satellite debris. So one of the solutions that's put forward for the problem of casualty risks is just to design everything so that it demises completely in the atmosphere. Okay, that's good for casualty risks, but it also is treating the upper atmosphere as a waste bin. And it just assumes that all that material can be deposited. More on that. There are a lot of different types of rocket propellants that are used for launches. So we're going to focus first on some of the launches here. And each of these have different effects that we have to take into account. Now, a lot of people, when they're thinking about kind of the sustainability and environmental aspects of rocket launches, people immediately go to CO2 because we're pretty much trained to do that, thinking about climate and so forth. But we really need to be thinking about climate drivers, and then it's not just CO2. So if we're thinking about RP1, for example, soot is a major component of the emissions from that type of rocket fuel. And soot has a major climate impact. It has a major effect on the climate system of Earth, and that cannot be ignored. If we look up here, the solid boosters, such as what's going to be used at the Vulcan, which is used SLS, the solid boosters have quite a bit of aluminum in them. And when you have the aluminum-based solid motor, that actually injects material directly into the stratosphere that depletes ozone. And this is actually very well known. It was studied as part of the shuttle program. You just punch a hole right into the ozone. Now, it's always been a very small hole. It's a very small amount of material that's lost for any single rocket launch. But now if you have a lot of things that are being launched using motors, solid motors, then there could actually be a larger ozone effect. And then things like water. people would be like, well, it's water. That's a green fuel. What can be the problem with water? Well, water is very common in the troposphere here, but it's a foreign substance in the upper atmosphere. And so that actually changes some of the chemistry. And we have to be very mindful of that. And so one of the examples of things that it could do is the water punches holes in the ionosphere through neutralizing it. And that's going to have some effects that we're going to show in a moment. Just to be mindful of where rocket emissions are placed, there's a huge amount, right? Let me take a step back. So here's the troposphere, okay? And then this is everything else. So the emissions are just placed in very different areas from what we're used to when we're thinking about, say, factory emissions, auto emissions, even aircraft. Aircraft are, for the long haul aircraft are right at the boundary of the troposphere and the stratosphere. So just rocket emissions are put in a very different category. All right, emissions aside, rocket emissions aside, let's talk about the satellite reentries. And this is something that hasn't been appreciated very well and is only recently being better understood, although there's a lot of work to do. So let's go to a system where we have 30,000 satellites, each weighing a ton. Okay, so I'm going to use just Starlink as an example here because it gives us a real anchor of a way to think about this. And let's have a 5-year replacement cycle. So if you do that, then there are going to be 6 kilotons of satellites disposed of per year, and there are 16 tons of satellites disposed per day. And now if we assume that all of that, and this is just from the one constellation, now if we assume all of that, ablates in the atmosphere, burns up, and let's say this is for safety reasons because you want to reduce that casualty risk, then we could just calculate what are the consequences of that. So if the mass is, say, 50% aluminum, then that's 8 tons of aluminum per day. Well, what does that mean? The environmental rate for loading of the atmosphere comes from predominantly meteoroids. And the average daily rate is about 33 tons of material. That's a lot of material, 33 tons. But rock is mostly oxygen. It's one of those things we tend to forget. And then it has a little bit of iron and silicon and magnesium and all those other elements that are put onto it. And there are natural metal layers in the atmosphere. And all this chemistry has come into equilibrium to create the situation that we know of as the Earth environment. If we look at things like aluminum, it's only like 0.3 tons per day of aluminum. So we're already an order of magnitude plus above, or this constellation alone would place the aluminum deposition or order of magnitude above what happens naturally. Lithium is already going to be several orders of magnitude above the natural meteoritic rate. And that's going to come from alloys and also lithium in batteries. And this changes the metal layers in Earth. Okay, well, what's the consequence of changing the metal layers of Earth? And this is all fine in theory and back of the envelope calculations, but like what's actually happening? Well, there's already evidence that we are changing the aerosol composition of the stratosphere. And this was done through some recent sampling through a program jointly run by NOAA and NASA in the US. And right here, this is then the chemical composition of an aerosol that has meteoritic abundances in it. And this is very well known. But what they found when they started sampling very recently is that 10% of the aerosols had very clear, just kind of smoking gun signatures of spacecraft components. And this is from the aluminum abundances, which were just outrageously high, lithium abundances, copper abundances, and niobium abundance. It's weird. It's a weird aerosol, and it can only be explained by spacecraft reentry components. What does this do? Well, it changes then the chemical composition of the aerosols. And if we keep going at the rate that we're going, it's not going to be long before we actually have a very large fraction, many, many tens of percent going toward nearly all aerosols of having some spacecraft components in it. That changes then the properties. Aerosols are a very important part of the climate system on Earth. And, we don't know what we're doing to that very important part, because we could be changing the reflectivity properties of it. Overall, we have, when you deposit soot in the atmosphere, that heats the stratosphere. While it actually cools the troposphere, it heats the planet overall, but it's heating up the stratosphere. And that changes the ozone equilibrium abundances. Alumina can create surface, can be a place for surface interactions that create ozone depletion. And if you have things like water and other aerosols that are being deposited in the upper atmosphere, you get things like mesospheric clouds, which have a whole bunch of different implications. The ionospheric holes that I mentioned create different types of sky glow. And so basically it's allowing charged particles to then enter deeper into the atmosphere. And also when it recombines, it creates then a glow like you would have for aurora. So you're actually changing then the night sky as a result of these holes. And so the occasional one is okay, but you start having lots of them and it's a problem. Okay, where do we go from here? All right, so we very much want to build these space technologies, but we absolutely have to understand that there is an environmental cost in doing so, and you have to make the designs that account for that. Now, we may be very much tempted to just find a tech solution for this. We could just tech our way out of the problem. Well, that's not going to happen. So these are types of problems that require innovations in governance along with technology. There are lots of different paradoxes that arise, such as Jevons paradox, and we have to make sure that we avoid those type of things where you increase the efficiency of the use of something, and as a result, just more people want to use it. And so all the benefits you have from the increasing efficiency are counterbalanced, at least from the environmental aspect, by the increased use. And ultimately, what we're doing is we're going to a consumer electronics model for satellites. Lots of benefits for that, but it also means we have a lot of waste, and we're treating the upper atmosphere as a waste bin. And we have to recognize that that's what's happening, and so that we could design systems that have many of the benefits of the rapid replacement without actually harming the environment and our ability to continue to use your space system. So steps forward is that we have to recognize that there is a space system. We can't just ignore it. We do want to have a multi-level governance approach. We do want industry to help with this and establish best practices in good faith, not just best practices to beat competition, but actually things that move everyone forward. We need smarter regulation that takes into account cumulative impacts. International cooperation is needed. We can't have flags of convenience. That's going to be a real problem with getting our handle around this. We need an even playing field for everyone. And ultimately, we have to understand that the Earth space system has limits, and that we need to maintain and recognize what those limits are, which will be a combination of rates and numbers. And it's going to be evolving as things change and our experience changes, and we have to be nimble with that. But we can't ignore it if we're going to continue to seek the benefits of space systems for society. And I'll end there. Thank you.
Thank you very much for your excellent presentation, Dr. Aaron Boley. I can see we can maybe some questions asked through the Q&A chat box. Maybe we can have around two questions answered. The first question I can see from there is, do present-day satellites have collision avoidance systems on board?
So one of the things that we often hear about with the reports are such as the automated collision avoidance with, say, the Starlink system. It is my understanding that the Starlink system still uses basically knowledge from the catalog in order to make those decisions. So it's just basically improved decision-making on the ground that's then done autonomously. There is progress toward using, recognition of kind of the orbit before a collision and recognizing whether you need to move. NEOSat has done a lot of excellent work on that type of thing, but I'm going to defer any further comments to some of the other colleagues who are giving presentations, because they may be better suited to answer that.
Great. Maybe another question. from the audience is, what is the status of global regulations and ITU requirements? So ITU is International Telecommunication Union, I
Yes.
assume.
Yeah, no, it's a great question. So, there are different levels to this. Ultimately, right, the Outer Space Treaty actually is a really interesting and flexible piece of international law that sets the foundation of outer space law. And I see another kind of question here about the recent Russia veto. I could comment on that in a moment. But the under the Outer Space Treaty, it makes all actors then kind of accountable by their launching state. And so whether you're a commercial actor or whether you're a government actor, you're launching satellites, your state has to supervise and authorize those launches. So there is actually that's a really fundamental part of kind of the way space law is organized. There's also a due regard clause under Article 9, as well as a clause of non-interference. And it's basically, it's trying to foster people to have to cooperate and work together. The problem is the specifics of those terms, where it's both a feature and also a bit of a bug. So the feature part of it is that it's adaptable, so that as we change our behavior, we can kind of redefine what due regard, really means. The problem of that is states are using the ambiguity in the terms to kind of do whatever they want at the moment. And so that, there's a lot of potential that as practices move forward, and this is where things like industry could really play a fundamental role, is that it could really kind of force the hand of states to take on best practices very rapidly. And we are seeing some of that change. ITU is also another place that plays a very important role in coordination, but they still require on states to actually do the authorization. And as for this recent veto, so there was actually a poison. This gets into geopolitics ultimately. There was a poison pill that was put into that. So China and Russia have been trying to put forward then rules against the militarization of space and the use of space weapons. And there are things that the United States objects against that. And so there were certain things that were put into this that just made it that was upsetting to Russia, because it kind of went against what they're trying to do in another way. So like no one here is like the best actor there. It's a geopolitical struggle is the way to take that. So it's not that they're trying to inherently rule back the premise, basically Article 4 of the Outer Space Treaty.
Thank you very much, Dr. Boley, again for your presentation and your answers to the questions. So we can answer question, have some time maybe at the end of the workshop to answer questions, but we'll log all the questions so that we can respond offline afterwards.